Okay, folks, well, it wouldn't be the last set of videos without some of the organ music in the background. So we are on our last topic of the semester, and it's a pretty straightforward topic compared to some things we've done this semester. So great job. This is our week 6 of 6 online, so keep it up. We are doing great, and we are now officially in the home stretch. Okay, so I'm using the slides. So this is Roman numeral 8, not that it matters, and we are revisiting thermodynamics here. So I think what I'm going to do, we'll see how it goes with time, is chop this up into qualitative video and then quantitative video. And ultimately we'll connect a little bit of this to equilibrium, but not that much. Okay? So and the first topic that we've done here, you've already done this one. So under letter A, I'm gonna really streamline this. So letter A is the basic concepts, fine. So that's the basic stuff. Sorry, this marker's running out. So basic concepts, maybe I'll switch over and try this blue one. Hopefully you can see this. So the basic concepts here, and I'm really gonna whip through some of this first stuff, because the first one you already know, enthalpy. Okay, and the first law of thermodynamics. You already know that stuff. If you want to copy all that down, go ahead. So enthalpy is the same as heat under constant pressure. We use the symbol delta H, and if it's positive, it's endothermic. If it's negative, it's exothermic. If it's 0, it's isothermic. And you use the thermodynamic tables. Now you're going to want those. I uploaded those onto D2L. In the back of the book, there's also a table of thermodynamic data. You're going to want to have some reference of those thermodynamic tables while we're doing this whole last section. So make sure that you have that. So under letter A, number 1 and 2, I'm actually not going to do that because you can just write that down. And you might remember for, I'm really streamlining. So 1 and 2, just copy that down. Just copy that stuff down. And you might remember to calculate a delta H, we add up the heats of formation, so from the table, of the products in a chemical equation, so we have to know the balanced chemical equation, and we subtract from that the sum of the heats of formation of the reactants. So that's a skill we want to go back and make sure that we do, because we're going to do this for each of the 3 variables we're talking about here. Okay, so you look that up in a table. So a simple example is vaporization of water. So liquid water in equilibrium with actually gaseous water. And this is vaporization, so we'll call this the enthalpy of vaporization. Oh, by the way, it should be positive, shouldn't it? It should take energy putting into water, liquid water, to turn it into a gas. It should be a positive number. And you look up, I'm just going to go right to the numbers. You look up the heat of formation of gaseous water and subtract from that the heat of formation of liquid water. Make sure you're paying attention to which state of matter it is. So the heat of formation of gaseous water is negative 241.826 kilojoules per mole. I really should multiply by 1 mole because it's 1 and 1. Minus the heat of formation of liquid water, which is negative 285.840 kilojoules per mole. I said this is going to be qualitative, didn't I? But this is just a reminder. So you get the answer of positive 44.014 kilojoules per mole. This is a review. You may want to fast forward this. So that would be the heat of vaporization, just incidentally. The delta H, not of vaporization, but of condensation, going the opposite direction, would be negative. That, just so you know. Okay, so that's a review of enthalpy. So we need that variable. Enthalpy is one of our 3 thermodynamic variables we're going to need in this section to reconnect to equilibrium. So make sure you understand how to do that through a balanced chemical equation. I'll give you plenty more examples, but I'm not going to work them all because I want you to get a little more involved in these videos. The second thermodynamic variable is entropy. Now, I know we defined this already. Oh, I put a picture on here. One of the scientists, he actually just passed away recently, associated with entropy is Stephen Hawking. He's now interred, which means his ashes are interred, in Westminster Abbey in London. And I'm just, before we keep moving on, I'll make sure this blue is appearing okay. Yeah, it's okay. Okay, so go ahead and copy down all that stuff about entropy. And we've done some of this before. Yeah, we did this before. Entropy is a measure of disorder. If you create more disorder, that's an entropic process. If you create less disorder, more order, kind of a double negative, that's an entropic process. And if there's no change in entropy, no change in disorder, that's an isentropic process. And we're actually going to do the exact same thing here. Sorry, I keep staring at the notes. So just copy all that down. And the second law of thermodynamics, which we're not going to dwell on too much, it's actually really important for biology as well as for chemistry, is that the entropy, the disorder of a closed system, I think that's the way we worded it here. Yes. Yeah, well, entropy tends to increase for a closed system. It's just sort of the natural tendency of entropy, which is balanced with enthalpy. It's more of a philosophical discussion. I'm not going to get into that here. And then the third law of thermodynamics is that the entropy of a pure crystalline solid at 0 Kelvin is defined to be 0. In fact, I put in my notes here, take a look at the entropies on that thermodynamic tables, and you'll find like, what are some of the really, really small entropies on there? Things that are solids, because they don't have much disorder. So just kind of take a look at those entropies, and we're going to use them in exactly the same way. So entropy, disorder, and the math is exactly the same. We're going to take the entropy of the products minus the entropy of the reactants. It's always final minus initial using those tables. So the math is exactly the same. So maybe we can streamline this. Just know what you're calculating. If you get a positive delta S, that's more entropy, positive delta S. If you get a negative delta S, that's less entropy. So it's more order. Okay, I want to show you some conceptual examples. We'll do a couple of math examples, and then we'll go from there. So I lied, this is not a conceptual video. So we're now under entropy. And I don't like the way that blue appeared, so I'm going to switch back to this black one. So there's entropy. You can write those down in the notes. So conceptual entropy, and we use the symbol S there. And I'm just going to kind of crank through some of these. So if you have liquid water turning into gaseous water, where do you think there's more disorder, in a liquid or a gas? Well, okay, actually, you know what? I'm going to extend this out. If you go from a solid to a liquid to a gas, that is more disorder, which we symbolize with a positive delta S. Make sense? You're making a more disordered system. It's more chaotic, if you will. It's more motion, more random motion. There's another better way of saying it. Down here. So states of matter changes. Solids, liquids, gases. We're not doing plasmas and Bose-Einstein condensates here. But something where you might see a little bit different. So that's example 1. Example 2 I have is what we've always done with the ammonia synthesis. It's important to pay attention to the state of matter. Okay, so they're all gases, it's not a change of state, but where do you think there's more disorder? Is there more disorder here or here? This kind of goes back to the calculation Kp, Kc we did. You have 4 moles of gas here. You have 2 moles of gas here. So this actually is a, well, let's see. We're going from disorder to order. So this is a negative delta S. More order. Okay, that's actually hard to do because nature tends to want to go to more disorder if you leave it alone. You don't intervene with it, putting in energy. The thing is, in biological systems, you're always putting in energy because of metabolism. So in this case, it's a negative delta S. Okay, and I think that's the only example I'm going to give you here. Maybe one more. We're going to build this variable in quantitatively later. How about you consider steam, water vapor, right at the change in state temperature, 100 degrees Celsius, versus 150 degrees. Well, what if you do that? Well, that's going to be a positive delta S, more disorder. Because there's more motion, there's more kinetic energy, so you're creating more disorder when you do that, based on temperature. So that's another variable we're going to bring in later on. Okay, and you know what? I'm gonna really streamline this. That's conceptual delta S. Quantitatively, it's exactly the same. So if you want to know the delta S of any process, you add up the entropies. Now I'm pretty sure in the book, yes. These are not labeled as delta, like delta S formation. Why is that? Because we have an absolute entropy of 0 for a pure crystalline solid at 0 Kelvin, excuse me. So we don't actually have a delta here, it's a straight up S. But these are all at 298 degrees Celsius, that's standard temperature, standard pressure, but it's the same math. Add up the entropies of the products. Fine, balance the equation. Subtract from that the entropies of the reactants. Okay. Well, let's just do 2 of them. I think that's enough. So you balance the equation. Fine. Okay. And you then do that math and get an answer and then interpret it based on the concepts. Sorry, the organist is getting pretty vigorous. So for water and for ammonia synthesis. So what we're going to do for water is take the heat of vaporization of gaseous water, the entropy of gaseous water minus the entropy of liquid water. So we're going to take 188.72. Now here's a chance for me to introduce the units to you. The units for entropy are actually joules per mole times Kelvin. Why am I saying it so emphatically? Because eventually we're going to want to turn this into kilojoules. So get used to doing this. Calculate a delta S and then divide by 1,000 to make it into kilojoules. That was my divide by 1,000. My computer screen's about to go off. And then we're subtracting from that that's gaseous water, then liquid water is 69.94 joules over Kelvin. Well, it doesn't matter if it's Kelvin times mole or mole times Kelvin, to be quite honest. And you end up getting a delta S of positive, which we expect, because we're going to something that's more disordered, positive 118 joules over moles times Kelvin. Which then, if you divide that by 1,000, is positive 0.118. Yeah, I'm just going to leave it like that. 3 sig figs is fine for this. Kilojoules. See that? So it's the same math. Make sure you interpret it. So if we're vaporizing water, it should be a positive, it should be creating more disorder, positive entropy, and then turn it into kilojoules. Now ammonia, okay, I guess I'll write it out for you. Why not? We have to take, let's see here. Well, I'm just going to talk it through. We're going to take 2 times the entropy of ammonia, okay, minus the quantity 3 times the entropy of hydrogen plus 1 times the, okay. Well, you're going to end up taking, maybe you just listen to me do this one. So 2 times the entropy of gaseous ammonia, that's 193. And you know what, I'm going to streamline this. The units are joules over mole Kelvin. So we're going to take 2 times 193 minus, we have 2 things to account here. So 3, because that's in front of the hydrogen, 130, the coefficient I mean, times 130.6 plus 191.5. And we know this is going to be negative because we're creating more order, less entropy, negative delta S. So I think I have that right. So it's products minus reactants like always, and you end up getting a delta S of negative 197.3 joules over moles times Kelvin. And that ends up being negative 0.197.3 joules over moles times Kelvin. And let's see, that might be a good stopping point. Yep, I think that'll be a good stopping point, folks, is entropy. So make sure you know your definitions. Enthalpy, plus minus 0, entropy, plus minus 0, be able to do the math for delta H, be able to do the math for delta S, and then make sure that the units match up. Delta H, the units will be kilojoules per mole. The units for delta S will be joules per mole Kelvin. We have to take temperature into account later. Just get into the habit of dividing it by 1,000 so that the units, oh, I made a mistake. Just get in the habit of, oh, I forgot those. Oh, no, I didn't forget it. Just didn't write it very carefully. And make sure that you keep track of the signs and everything. Because what we're going to do in the last video of the semester, hopefully we can still read all of this, is we're going to take all these variables and combine them into one final variable, which is called free energy. So just make sure you can do these. There's some examples in the homework problems where you do them qualitatively, understanding what's going on in disorder order, where you do them quantitatively, that's fine. and then we combine them together in our last video of the semester. And that's it.